Hello, everyone. Welcome to this week's binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Just as a heads up, Friday this week we're planning to do some watch party streams on Offensive Con Talks on YouTube. So just check for notifications for when we do that. And we're also going to be taking our summer break in 2 weeks after the 30th and 31st of May. So those will be our last episodes for a few months. With that out of the way, we'll start off with the Spot the Vuln challenge, which I'll let Z get into.
Yeah, and I'll also just place a little bit of emphasis on the offensive con talks. Those will be over on YouTube, not here on Twitch. So just calling that out specifically. As for Spot the Vuln this week, this one is type juggling in PHP. So kind of a classic PHP style issue. It happens specifically, or in part, because the JSON decode of the raw post data. With JSON decode, you can cause the data password being compared on line 11. You can get that to be a Boolean value. Just using URL parameters, that'll always, like, if you enter true or something, that'll always come out as a string. At least in my test cases it would. So you can't really do this normally, but if they were to do this sort of JSON decode, or if you just are able to create the Boolean perhaps in tossing arrays, like, there are other type juggling issues that can come up too. In this particular case, when you're able to get that as a Boolean, this if statement on line 11, if data password equals the password looked up for the user, in that case, it's going to resolve to true equals, well, is this other value, the password that somebody has set, is that a truthy value? Somebody else called out the possibility of, like, a timing attack. We covered that a few weeks ago on, like, the practicality of timing attacks over the network, so maybe there's a chance on that. And of course, in the way this is written, the password's likely stored in plain text, which would be another pretty significant vulnerability, but the one I was really looking to showcase here was just the type juggling.
Yeah. And the name gave it away a little bit too this week with clowning around. But yeah, well, if you're familiar with PHP anyway. But yeah, I mean, it's an issue you don't really see too often in real world anymore at this point. But it might crop up every now and again. And
And
it's a fairly
PHP,
popular CTF type issue.
I mean, PHP has kind of taken a lot of steps to improve, especially with, like, PHP 8, to improve kind of the consistency of those implicit conversions that they do when you use the double equal instead of triple equals. So there has been some improvement on their side. But we have covered some vulns related to type juggling before. The last one that comes to mind was a JavaScript one. But they still crop up from time to time. It's just kind of a hazard of working with these very dynamically typed scripting languages where they try and make everything work.
Yeah. All right. So with that out of the way, we'll get into our first topic here, which is the secret club post on fuzzing Solana's rBPF, which I'll let Z get into here.
Yeah, I thought this was a pretty interesting set of posts, actually. There are two posts. Um, First one is really just about the fuzzing being done against this Solana target, where, I mean, effectively just talking about how they went into it, a little bit of the approach for rBPF. They ended up having um, effectively BPF, Berkeley packet filter. We've talked about a little bit when talking about something Linux kernel exploits in the past. This one, rBPF, written in or is a Rust virtual machine, providing both the JIT compiler and an interpreter for the BPF programs. And this basically is what Solana, if you're familiar with the cryptocurrency SOL, um, the smart contracts and stuff on there are written to run within this VM. So they're fuzzing in. They did some differential fuzzing, so they'd run the same test case against the JIT versus the interpreter. If they had a difference of opinion on what the results were, or if one crashed, one didn't, something like that, that difference would be used to indicate that something went wrong in one of them, because they should always be consistent. So what they found were two vulnerabilities. Neither of them necessarily leading to code execution, but I still thought they were interesting to talk about. First bug here was a resource exhaustion, and the bugs. So the first post of this talks about the actual fuzzer and some of the implementations of, like, background information. Second post is about the 2 bugs that they reported. So this first one, resource exhaustion. And they called out as like, this is a testament to the incredible complexity of inputs a fuzzer can discover. The input test here, if you're watching, see, is just a entry point and then so start of the program and 4 lines of actual code. Iterate over R0, just adding 255 every time to it. If R0 is less than, A3, big number or biggish number, go to my so basically go back to the last thing, just keep repeating that over and over until the number gets big enough. These values do kind of matter because what this ends up doing is these 2 lines, the R0 and the if statement, will result in 65,534 instructions being executed. And I should mention this program resulted in a memory leak, so combined that can lead to the resource exhaustion. I'm now getting into how you ended up with that memory leak. So going back onto that, you've got these 2 instructions. Every Solana program is limited to 65,535 instructions. So that's why it kind of matters that this thing iterates until just about to that limit. It executes, and then the loop will end, and it gets to the next calculation, which just comes out to being a 0 every time, because R3's never been set, so shifting it by anything's still going to give you a 0. It's just a random instruction. Hits that is the last instruction within the limit, and then call -1 is the last instruction. And that's going to take it right over the limit. But first, what ends up happening is you have call -1. -1 is meaningless. It is a unresolved symbol. It doesn't know what that is. So when you make this call, it's still going to make the call, and it's going to get this unresolved symbol error. Sorry, I've kind of skipped over one other little check here that kind of matters. I just talked about the limit of how many instructions everything can run, or how many instructions the program can run. That on the JIT side of things, so when this gets kind of pre-compiled to some x86 code, it's going to insert those checks on how many instructions have been executed at the end of every basic block. So basic blocks are effectively just code that once you start it, block of code once you started, you're going to end it. So that would mean that the first basic block you enter in this entry point, it's going to run through these 2 instructions. The R0 and the if statement will always be executed together. They're one block. And then the calculation, the other one or another. So at the end of both of those is where we'll actually check the number of instructions run. So with that in mind, goes through, gets really close to the limit to the first 2, makes this next one, and then makes this last call where it gets the unknown symbol error, and then finishes that call, and it notices, hey, I've executed too many instructions. Because they've executed too many instructions, it's then going to raise a different error about maximum instruction count exceeded, or whatever the error is. And that's where you end up with this memory leak, because the unknown symbol error would allocate a buffer and say hey, there's this -1. It would allocate the buffer for the -1 for whatever symbol you were trying to call that it doesn't know. It's here's this unknown symbol. What is this? And here's the buffer pointing to what the symbol was. And then when it writes that other error, the maximum instruction error, it basically just overwrites that pointer, meaning it never gets freed, and you end up with the memory leak.
Yeah, the reference basically gets lost before it can be cleaned up.
Yeah, so all of that in that's 4 lines of code, or 5 lines if you want to include entry point. And it's a good point of the types of bugs a fuzzer can find, because this is something that would be perhaps hard to keep in your head, but a fuzzer can come across this reasonably effectively. But yeah, leading to resource exhaustion. They paid out $100,000 for this because it's a denial of service bug.
Yeah, and I will say, like, most of the time, denial of service bugs are kind of brushed off and don't really have a high impact. But because you're talking about blockchain here, um, the impact is magnified a lot more, which is why you see that 100K payout.
Yeah, it's as Obj5 mentions in chat, they're interested how denial of service can be so high impact in the right context. I completely agree. That's kind of why we've covered a few other miscalculation bugs. I think there was some NCC group research earlier this year that we covered. And it's interesting, these normally pretty minor bugs can have a very significant impact just given this right sort of context where it actually kind of matters that there isn't denial of service. You can't just restart it and everything's okay or something. And smart contracts have really kind of changed the landscape a little bit on what type bugs. I mean, don't get me wrong, it's still like code execution matters, so it hasn't changed that. But other bugs have definitely somewhat greater importance, I guess. So moving on with the second bug, a little bit more straightforward to understand because all that happened there is that when optimizing or when performing a memory store, it's going to look up and be like, hey, can they write to this memory address, whatever. Um, and in optimizing or generating the output instruction for that, they would basically always compare using opcode 0x81. And that would include when using just an 8-bit operand to it. The problem there is that 0x81 is for 16-bit, 32-bit, and 64-bit comparisons, not for 8-bit. So if you were using an 8-bit, it would end up comparing it with extra bits included in there. It would be comparing it as a 16-bit, even though the intent was still just for the 8-bit comparison. So if any extra bits were flipped in that upper part, that can cause the comparison to be performed against the wrong memory region, basically. Or not necessarily the wrong memory region, but the wrong value, which has the implication of being in this memory access check.
Yeah, it's
So
basically a bugged range check because of emitting a bad opcode. That's
yeah,
essentially what's happening here.
yeah, that's a really good way to summarize it. Which is effectively what's happening. They did have it was a little bit tricky also to I guess narrow down. Maybe that's a bad way of putting it. But different Rust implementations basically end up dealing with this differently or having the bug show up because your debug builds rust on nightly or the nightly debug builds. All of those would end up having 0 padding with the fields, so basically wouldn't show up. It would always be 0. But the main builds, the production builds that went out, those would have those could have the bug. So it was something that couldn't be easily spotted if you're just using the test versions. Which is one reason why it probably wasn't discovered sooner.
Yeah, I'm guessing it's one of those situations where the overhead of zeroing it out was too significant to be used in production builds. Especially when you're talking about JIT and like these optimization routines, the performance is a bit more key there. So, yeah, it seems like one of those things where optimizing it for production builds and not doing that zeroing was what ended up allowing it to be exploitable there, which is kind of a problem because a lot of testing is done against debug builds. So, um, yeah,
Yeah,
that's a little bit of an interesting aspect to it.
it's a bit of a challenge because debug builds do often have different memory layouts. Maybe extra fields end up being included in certain structures for debugging purposes. There's a lot that changes in debug environments. So this sort of thing, while having a consequence that matters, isn't super common. The fact that there are differences, or the fact they might have padding or even extra padding, red zones or whatever in other areas, you're not going to put those in production, and that means there are differences. There are bugs like this that can slip through. And once again, for this one, they got another $100,000 bounty out of it. They disagreed with that. So actually exploiting this bug, and this was why, or part of why, Solana kind of downgrade this from what the author was expecting to get paid. They mentioned they were expecting like $1 million or at least $400,000 bounty on it. And that's because to take advantage of this vulnerability, It exists, but you would need, because you're basically able to write to the read-only data, or potentially write to read-only data, you still need a program with the sensitive read-only data that you shouldn't be able to write to, running on chain, that also gives a user kind of access to the offset to be able to mess up this calculation. Um, so it does have some dependencies there. I don't know if I agree with calling this calling this a denial of service bug. It feels a little bit disingenuous to me. Um, I don't necessarily fault Solana for not paying out $1 million bounty on it. I have not looked at their bounty program, so I can't really comment on how clear it is and stuff. But as the organizers of the program, like, they do kind of get the ultimate final say on that, and I can kind of respect that. But it does sound like there might be some reason that they should clarify exactly what they're willing to pay out for, because it does feel a little bit disingenuous to classify this as simply denial of service. At the very least, I can agree with the author on that, but I don't know enough to, I guess, comment on the details of it.
Yeah, and since we're getting into the payout, it's also worth noting that they ended up donating their earnings from this bounty to I believe it was, Texas A&M Cybersecurity Club, and Solana was kind of accommodating there too, because usually with these cryptocurrency based companies and their bounties, they pay you out in the token like of that company, so in SOL. Although in this case, Solana actually paid out the bounty to the Texas A&M Cybersecurity Club in U.S. dollars, which makes it easier to deal with from like a tax perspective and stuff like that. So yeah, it was kind of cool, just seeing the charity donation and some of the uh, cool steps that Solana took there. But yeah, beyond that, I mean, the bugs are pretty cool too, and like we were saying earlier, the impact is kind of unique when it comes to blockchain stuff. So these bugs are a lot more significant than they otherwise would have been.
Yeah, and frankly, great bounties for what they say is just a weekend of fuzzing.
Yeah, I mean, pretty good rewards there for sure. All right, so we'll get into our next post here, which is a post on exploiting a very old use after free in Python 3 in a way that's portable across every version. The UAF itself goes back to Python 2 days and is sort of similar to some browser bugs and how it works. The POC is at the top of the post here. They go into some deep detail in the background of Python objects and the internals, but to understand the POC, basically what you need to know is that a buffered reader will end up taking a raw IO based binary stream, and of which you could basically specify your own, like they do in this POC. They have this class file which implements a raw IO base. Um, and when that buffered reader gets created, an internal buffer gets allocated. And when you read from the buffered reader, if there isn't any data and available in the buffer, it'll try to fetch it from the underlying stream. Um, somewhat standard there. The problem is you can specify a read into method in your custom raw IO based class, which will back up or save the buffer to a global variable. Then when you go to free that buffered reader, that internal buffer gets freed, but you still have a reference to it because of your custom handler's shenanigans of backing up the buffer pointer. Basically, this is a failure to track the references to the internal buffer. So yeah, I mean, it's kind of similar to some of the older browser bugs in the early days before the reference counting and stuff or the reference tracking um, got properly handled. So the way the POC exploits this is by overlapping a list with the UAF view, and then they use the view to write a null pointer into that list first entry to cause a null deref. Um, Obviously, null deref isn't really that useful, but when you have a situation like this where you have a view allowing you to corrupt internal data structures that overlap it, there's a lot of ways you can go and a lot of potential primitives you can derive, depending on what objects you choose to overlap and such. First order of business here was to derive an info leak, which they did by crafting a fake byte array. Um, Basically, what they did there was they used a bytes object, which has like a header and then has an auxiliary data buffer. So they have arbitrary control over bytes inside of it.
Yeah, and just
Kind of similar to JavaScript.
Um, one place where this gets a little bit confusing is you've got the bytes as if you've used Python, if you've ever written like a B string, where you do like B and then start your string, like that's kind of the bytes he's talking about. That's separate from the bytes array as an object type. Bytes and bytes arrays are, while they kind of have the same thing. As Spectre was just saying, the byte strings you'll have your data exactly 32 bytes away from the start of it or whatever, like just a little bit of header. They are also different objects. So a little bit of confusion around that. Sorry. Go ahead, Spectre.
Yeah, all good. So yeah, they crafted a fake byte array inside of a bytes object, and then they could get a reference to it by using the ID method, write that into the view array, and they were able to use that to leak the contents of the freed memory location, which would include pointers and such, and they were pretty easily able to defeat ASLR by using
Um,
that fake bytes array object.
so yes, they were able to defeat ASLR with that, but it wasn't that they could read into the freed array. They already had that. They have the ability to read into the freed array just through let me scroll back up here. This view object. That view object gives them read and write right into that array. Anything else that goes and grabs it, they can read and write through that. That view thinks that that freed memory address is just a bunch of bytes that they can access and write to freely. So they kind of have the read write primitive of that specific memory really easily. And then the list is, it thinks list is seeing that same memory but as a list of pi objects. So what they're able to do is when they craft the bytes array that you mentioned, they'll write the address of that bytes array. So yeah, they'll have the byte string with the bytes array crafted inside of it. They'll put the address of the bytes array or they'll write that into the list as like the first element or whatever. And then when they access like view 0, instead of having a null pointer dereference, they're going to be accessing that fake object. And that bytes array object has a structure inside of it. That's just a pointer to whatever memory you want to access. And then accessing through there is where they're able to get access to arbitrary memory.
Yeah.
You
So
can go
what I
on
was
with that.
getting at, yeah, what I was getting at there was where they talk about the final leak primitive. They state that they got it pointing to the freed heap buffer, and that's kind of where they're able to leak the pointers. And then they have the arbitrary read-write capability to be able to read wherever they need, which is kind of important for a bit later on in the chain. But yeah, I'll get to that in a little bit. But yeah, once they have the memory leak, they wanted to go for PC control, obviously, which they did by crafting a fake pi object, kind of similar to the leak strategy. Um, that object contains a pointer to a V table, which, whenever you have a V table, that's obviously a very juicy code execution hijack target. So yeah, they were able to write a fake V table, get code execution. To make it portable, because this actually runs across all different versions of Python 3, they basically use the arbitrary read primitive they have to parse the elf headers, and they dynamically get the offsets of what they need from the relocation table, which I thought was kind of a neat trick. Um, it's always nice getting into some of the elf internals and kind of abusing that to get a dynamic exploit in this way. So yeah, I thought that was kind of cool, and I wanted to call that out. But
Yeah, I'm
yeah,
a
I
fan
mean,
of seeing
fairly
them.
straightforward exploit as far as these types of language bugs go.
I'm a fan of seeing them kind of worry and deal with the portability of an exploit, because oftentimes we have the exploit that um, maybe they're going to use the address of something that just happens to be located nearby or something, and like that's great, but I don't know. I appreciate when they take these extra steps to actually make it extremely portable, because there is extra effort involved there that we don't talk about very often, which is what they went into here. I thought this was a really good post on the whole. The bug itself isn't too complex. The strategies involved aren't all that crazy, but a pretty straightforward well written post, regardless.
Yeah. Now, you know, the impact here is pretty limited because you need to already be able to run arbitrary Python code to exploit this. You're not really gaining any privileges. But the author does point out in the conclusion some places where this might be useful, such as like bypassing some sandboxing through the use of like audit hooks or whatever. Not a situation you'll really run into all that often. Usually, if you can run Python, you can get code execution pretty easily. But still, it's fun to see memory corruption in language parsers and language engines. Um, and yeah, there's a lot of cool internals under the hood that you can use to your advantage here. So the impact here doesn't really take away from how cool the exploit is, in my opinion.
Yeah, no, I mean, as a post, I did not really worry too much about what the actual impact was. Like as an educational post, I think this is really well done. Um, in terms of impact, yeah, maybe it's not the strongest impact. There aren't a lot of places where you have, like, unlike PHP, which does get run a lot in those shared environments. And PHP has its pseudo restricted environment thing. I forget what it's called right now. Python doesn't really have the same. It's generally offered with, if there is sandboxing around it, it's, like syscall sandboxing, not like in language. So the impact isn't there, but I I think this is a really good post illustrating kind of use after free and a little bit of like the idea behind type confusions. So I really liked it for that aspect.
Yeah. All right, so we'll get into our last topic here, which is one of the major vulns that got published last week, which was a PlayStation Hacker 1 bounty, which detailed a remote kernel heap overflow in the PPPoE driver of the PS4 and PS5, um, which PPPoE is like point to point over Ethernet or whatever. Um, which is this module or driver is borrowed from NetBSD, which kind of explains why there's a bug here, I guess. NetBSD typically isn't the best in that department. Remote is an interesting term in this case because it does require that the console be hooked up to like a PC over Ethernet to exploit it. But yeah, you don't need like local code execution to exploit the bug, or at least not to trigger a crash. To exploit it in a useful way, you might need local code execution. But yeah, the bug here is just the fact that it's possible to have a packet length get calculated in PPPoE send pattr for sending PADR address packets, and it's possible for that length to end up exceeding the max length of MCL bytes, which is 2048 bytes. Um, and that's a problem because PPPoE get mbuff, which they use to allocate an mbuff cluster, will simply truncate the length of the allocation down to MCL bytes if the length is larger than the specified MHLen. Uh, and now, granted, it's not possible to send one PAD-O packet that would exceed that MCL bytes max, but you can end up sending two with different tags. You can use the AC cookie tag and the relay SID tag to end up combining them to get like a 3000 byte or a 2800 byte in this POC um, length, which will end up getting put into a 2048 buffer. Obviously, that's going to exceed and heap overflow. Now, a lot of people got excited about this report, understandably, but there is a few things notable on this bug when it comes to exploitation. For one, in the impact section, MoonBSD notes that it's a possible RCE, and above that actually states that actual exploitation will require a debugger, which I do not have. Basically, what I'm getting at there is it doesn't seem like this is confirmed to be exploitable, which actually made it a little bit surprising to me that Sony paid out 10K here. But I digress. The other thing of note is this is ultimately an 800 to 1K byte overflow in the mbuff zone. You're somewhat limited on how much you can overflow because the MTU is 1500. So you can send like up to 3000 into a 2048 byte buffer. The mbuff zone is kind of a special zone because only mbuffs and mbuff clusters get allocated there. You're never going to have general purpose allocations from like some syscall that's going to end up in the mbuff zone. So deriving primitives is not going to be straightforward. You might have to try to manipulate the page allocator into giving you an adjacent page that's used for some other zone or like general purpose allocations. Maybe you could do something with the headers of the mbuff clusters. I'm not totally sure. But even then, on the PS5, the mitigations are pretty strong. The PS5 has KSLR, which PS4 does too, but it also has supervisor mode access prevention, execution prevention, and it also has CFI in the kernel. So if there's any pointers that you would have to fake in the headers, which there will be, if you don't have an existing leak and a way to get memory you control into kernel memory, you're not really going to be able to fake those pointers. So exploitation is going to be made a lot more difficult by that. Um, so
Speaking of
yeah,
the leaks, how much? Sorry, you know what? Never mind. Actually, I've already thought through what my question was going to be.
all right, all good. So yeah, I doubt this could be full chained on its own against the PS5 at least. I feel you'd need like an info leak to be able to use this effectively. On the PS4, this could possibly be used, but the thing is, this was patched in the 9.03 firmware of the PS4, which I kind of showed in a diff on Twitter. And I think this ultimately will be less stable than the existing exFAT exploit. So I don't think there's really much point in doing it on the PS4, except for just for something to do, I guess. Um, but yeah, so I'm a little skeptical on how useful this vulnerability will be. Um, but it's kind of a cool bug. It's not really an attack surface that I had considered. Like I never even really thought of PPPoE and thought to look there. So yeah, I mean, still a cool report. I'll bring up the diff here for anybody that's watching that's interested. So you can kind of see the bug fix here as well. So basically, what they did in PPPoE get mbuff, they check if the length is greater than hex 800, and if it is, they return a null. They don't allocate an mbuff, and that triggers a failure case. So yeah, very straightforward patch, and that's in 9.03 on the PS4. So yeah, um, bit of a weird bug, and one that I think would be tricky to exploit. And even if you did manage to exploit it, I think the stability would be questionable. But maybe it's worth looking into just for the PS5 aspect of it. But like I said, I think you're probably going to need an info leak to chain with. Nonetheless, that got reported to Sony and yielded a 10K bounty, so pretty good for MoonBSD still.
Yeah, and I mean, you might still need an info leak, but that is kind of par for the course with a lot of exploits. So might not have one now, but well, if there was an info leak, I imagine this could still be used over on the PS5. Like, it would still be a reasonable thing to use.
Potentially, yeah. The thing that's like a little bit worrying there is just the fact that you're stuck in the mbuff zone a little bit. And I don't know on the PS5 if you're able to manipulate the page allocator into giving you an adjacent page for like a different zone. Because the way memory allocation works in FreeBSD is super interesting. It's basically like pegged to the core a little bit. So like one core won't be able to allocate from the same set of pages as like another core. So it's a little bit weird with how the memory allocation works there. Yeah, I don't want to say that it's impossible to exploit, but it wouldn't be trivial. Even if you had like an info leak or something. So
Okay, fair enough. I was just thinking that, if info leak was the only thing kind of standing in the way, then that seems pretty reasonable that eventually an info leak will be found.
yeah, one thing that we've seen from like the vulnerabilities that have been published that affect the PS5, like exFAT for example, too, is mitigations go a long way into making exploitation difficult or maybe impossible for certain bugs, or at least requiring an additional bug on top of it. Because yeah, on PS4, I think this would potentially be exploitable on its own, but when you have CFI and SMAP, especially SMAP and SMAP are big. Um, yeah, it just it narrows your exploit conditions pretty significantly, and that's
Does
being
the
demonstrated pretty well by the PS5.
does the PS5 have XOM?
It does, yeah.
Yeah, so I
So
mean that makes hunting a little bit harder because even if you have a leak, you can't like dump the kernel to get all the code and hunt for other bugs.
yeah,
Um,
it's not super relevant for this vulnerability
no,
specifically, but yeah, the PS5 does have read only memory or sorry, execute only memory in both userland and kernel. So even if you were able to pop the kernel and get code execution there, you couldn't dump kernel. And like you were saying, yeah, that significantly limits your ability to perform vuln research to
yeah,
try to find better bugs to work with.
kind of thought for a while like XOM's a really interesting mitigation. But like you're kind of saying, like it doesn't stop a lot of exploits, but it is a mitigation. It is almost like the security through obscurity in a sense. It's just making it harder to actually get that code to do further research or to do like more effective research, rather than actually mitigating the exploits itself. So, oh no, came to mind while we were talking about the PS5. It's one of the few cases where I think of XOM actually being a pretty useful mitigation.
Yeah, because in a lot of circumstances, you can dump the code pretty easily. It only really works in like this really locked down environment, like a console. But yeah, in that specific circumstance, it's very effective. Another area it could be very effective is like IoT. If you have some IoT device that you don't want people to be able to dump the firmware and try to mess with, you can use read only or execute only memory there. Don't know why I keep saying read only because
Yeah,
that's
read
the
only
opposite.
is not. Yeah,
Yeah. Um, but yeah, like you said, in the PS5, it's pretty effective. The other thing is because there's a hypervisor in play, you can't patch the kernel, the PS5 kernel, if you have kernel code execution either. So basically, what I'm getting at here is even if you do manage to exploit the PS5, your post-exploitation scenario is really brutal. Um, so yeah, it's a console that demonstrates pretty well how effective mitigations can be. Although we already kind of knew that. Apple kind of demonstrated that well with iOS and stuff too, which the PlayStation security model is kind of emulating a little bit. They're kind of going the Apple route and saying, okay, well, we can't kill all the bugs. We'll kill the ways to exploit those bugs. But yeah, still, it's always cool to see like new reports that come out for consoles. Being able to take advantage of or being able to exploit lockdown environments like that is very enticing. But yeah, this bug, hard to say really if it'll be useful. There's probably other bugs that you could try to look for that will yield much better primitives and have better stability. So yeah, uh, I guess we'll see how it goes with that one. Not much more to say there though. Just have to see how it plays out. So yeah, unless you have any final thoughts on this topic, Z, or any of the other ones, we'll go ahead and wrap it up.
nope, and no shout outs this week.
All right, cool. And yeah, B Hopper said nice find from BSD. Yeah, I totally agree. I know the way I was talking about it made it kind of sound like I was, shitting on the bug a little bit. But yeah, no, it is a cool bug, and like I said, it's a cool attack surface to look at. It's just a tough exploit scenario to be in. But yeah, with that said, that's everything that we have for this week. Thank you, everyone who tuned in. VOD will be up on YouTube and Spotify and other platforms tomorrow. Remember to follow our Twitter and join our Discord to join the community. That's also where we'll be posting the notifications for when we go live on Friday for the offensive con talks coverage. So we hope to see some of you over there. We did this before with DEF CON and we had a pretty fun time of it. So yeah, we want to continue doing that sometimes. And offensive con usually has some pretty good talks. So I think that'll be a cool stream. But yeah, as the emphasized at the beginning, that will be on YouTube, not on Twitch, just for copyright type reasons. And yeah, with that out of the way, we'll be back next week. And until then, take care.